Okay, so today's agenda is we are going to continue with the remaining two non-ideal effects in MOSFETs, that is tunneling, second is temperature dependence. Then we will discuss about MOSFET's parasitic capacitance model. And third is that we will start discussing about calculating on-chip area of CMOS implementations. So this is a broad topic, but at least we can discuss about um, what is called as pull-up strength and pull-down strength. So calculating on-chip area of CMOS implementations is a very interesting concept, but actually it has to go stepwise. We will discuss that. So yesterday we discussed about these effects, that is velocity saturation, mobility degradation, body effect, channel length modulation, and the remaining two we are going to discuss today. It is tunneling and temperature dependence. So consider not 3D, the 2D planar structure of an N-channel EMOS as shown below. Okay. Source, drain, gate, heavily doped N plus region, SiO2 layer, This is our body terminal. Fine. So all of us know that this is our channel length L, and this is the oxide thickness Tox. Right. So we already discussed about a topic called as technology scaling, and one of the types of technology scaling is called as transistor scaling, while other is called as interconnect scaling. So under transistor scaling, we have constant field scaling, also called as Dennard scaling, constant voltage scaling, and we have the lateral shrink, or it is also called as lateral scaling, or also called as a gate shrink. So we already discussed that when the transistor's dimensions are scaled down, okay, in technology scaling, also known as device shrinking, along with width W, length L, and the supply voltage VDD, Tox is also scaled down. Okay, so as Mosfet reduces in size, the oxide thickness Tox few nanometers. Okay, and please understand one thing, that the oxide thickness Tox is actually smaller than the channel length. If you see comparatively, while L itself is in few nanometers, say less than 20 nanometers, Tx is even smaller than L. Okay, now if a question is asked that technology scaling means reducing Tox, can you tell me what will be the limiting value of Tox? My question is, what is the limiting, or we can say smallest Back, what is the limiting or smallest permissible value of Tox? Yes, the planar structure is there in front of you. What is the minimum permissible value or the smallest permissible value of oxide thickness? It's very simple. It is equal to the molecular thickness of SiO2. I can say, since Tox is the thickness of SiO2 layer, Tox min is nothing but equal to thickness of one molecular layer of SiO2, which comes out to be 3 angstrom, which is equal to 3 into 10 raised to minus 10 meters, or in other words is equal to 0.3 nanometers. Okay, so since Tox is the thickness of SiO2 layer, the smallest permissible thickness or value of Tox is equal to the thickness of one molecular layer of SiO2. So molecular chemistry says that if you lay down one layer of SiO2, the thickness will be 0.3 nanometers. That means what? L cannot be reduced below a value for which the corresponding value of Tox goes equal to or less than 0.3 nanometers. Okay, that is why we can say hence the channel length L cannot be reduced below a value for which corresponding value of Tox will be less than equal to 0.3 nanometers. Hence, L cannot be reduced below a value for which corresponding value of Tox is less than equal to 0.3 nanometers. Okay, and fabrication engineers have found that it is found that when Tox equals 2 nanometers, the gate current Ig, which is not which is which should be 0, starts assuming increasing values greater than 0, okay? Because for all TOX less than or equal to 2 nanometers, the charges start tunneling through the SiO2 layer. This gate leakage current now becomes comparable to the subthreshold current. Okay, so when the oxide thickness equals 2 nanometers and below, the gate current, which should be 0, starts assuming increasing values above 0, because for all TOX is less than 2 nanometers, charges start tunneling through the SiO2 layer. That is why this topic has the name tunneling. So this particular tunneling of charges was actually found by two scientists, Fowler and Nordheim. That is why we say that since this so why not write this? This concept is known as Fowler-Nordheim tunneling. Discoverers, we can say this is Fowler-Nordheim tunneling. So Fowler-Nordheim tunneling is observed only in short channel devices. Okay, this is also short channel effect. Okay, now we come to temperature dependence. So temperature dependence basically is expressed as a mathematical model which tells us by how much percentage will the mobility of charge carriers vary with the temperature. So temperature dependence is not new to semiconductor world, because even we see that the leakage current in a diode, it doubles for every 10 degrees rise in temperature. Similarly, the base emitter voltage VBE, which is taken as 0.7 volts for silicon transistors, also shows a variation when the temperature varies. The semiconductor devices inherent inbuilt voltages and leakage currents are definitely a function of temperature, and even charge mobility also depends upon that. So we say that the relationship between carrier mobility mu and ambient temperature is given by mu of T is mu of T naught into T over T naught raised to minus K, where mu of T is mobility at temperature T degree Kelvin. Mu of T naught is a mobility at temperature T0 degree Kelvin, and K is called as a fitting parameter. Value lies between 1.2 to 2. Okay, so let us take a small example of how the mobility will actually reduce or increase. Will come to know. Let T be equal to 27 degrees centigrade equal to 300 degree Kelvin. T0, I'm very sorry. Let T0 be 27 degrees centigrade or 300 degree Kelvin. Let temperature increase by 10 degrees centigrade. So T equal to 37 degrees centigrade equal to 310 degree Kelvin. So mu of T is mu of T naught into T by T0. So 310 upon 300, and we will assume that the fitting parameter is taken as 1.5, somewhere in between. So can anybody tell me what is the value of this? Please calculate this. What is the value of 310 upon 300 raised to minus 1.5?
Sir, it's 0.9.
Okay. Comes out to be 0.95 mu of T naught. Okay. So we can see that mobility has dropped by 5%. Recalculate it now for 20 degrees rise in temperature. Let T increase by 20 degrees centigrade. So T is equal to 47 degrees centigrade is 320 degree Kelvin. So mu of T is mu of T naught into 320 upon 300. Tell me what is the value now?
0.91, sir.
So again we see, so mobility has reduced by about 10%. So we can actually tell that mobility mu varies inversely with ambient temperature. Okay. So now we come to the next topic, MOSFET's parasitic capacitance model. So consider 2D of EMOS as shown below. Okay, so we have source, drain, gate, and body terminals. Now there are capacitances which exist between these three. They are called as inter-terminal capacitances or inter-regional capacitances. We will draw them now. Okay, so this is called as CGS, between gate and source. This is between gate and drain, so CGD. Between drain and substrate, CDB, B for body. Here we have between source and body, so we have CSB, and this is between the gate and body, so this is CGB. So CGS between gate and source, CGD between gate and drain, CDB between drain and substrate, CGB between gate and substrate, and CSB between source and substrate. Okay, so we can mathematically write, because CSB, CGS, CGD and CGB are in parallel, so gate capacitance will be a summation of these three. So we can write down CG is equal to CGS plus CGB plus CGD. Okay, so gate capacitance CG is a summation of CGS, CGB and CGD. Okay, now depending upon the operating region of Mosfet, equation number 1 takes different forms. Okay, so region 1 cutoff. For cutoff we have VGS less than threshold voltage, and we have VDS greater than 0. Cutoff region, no channel is formed, hence CGS is equal to CGD equal to 0, hence Cg is now equal to only Cgb. Okay, so equation number 1, the first and the third terms become 0 because no channel is formed in cutoff region and the gate capacitance is simply equal to Cgb. Then we have region 2. It is called as linear or ohmic. For this, the condition is VGS minus VT is greater than VDS is greater than 0. Okay, in this case, what happens is that CGS and CGD are non-zero. So we say that CGS comma CGD are a function of VGS comma VDS. Okay, so in this case we can say that CG is now equal to CGS plus CGB plus CDS. CGD. Region 3, pinch off. So here we have VDS greater than since since channel is pinched off at drain end, CGD is 0. Therefore, gate capacitance is equal to CGS plus CGB. Okay. So there is a reason why I have not shown the body terminal separately from source. This clearly indicates that body and source are shorted. And in the initial lectures only, I told in the introduction of Mosfet that to zero. Okay, that is body and source terminals are shorted. Okay, so yesterday in body effect we already told that if VSB is greater than 0 and VT is greater than VT0. Okay, okay, hence as VSB increases, VT increases, hence a larger potential is required at gate with respect to source to achieve channel inversion. The above fact violates the purpose of VLSI design, that is operating the transistors at as lower as possible. Okay.